Now, we'd seen actually quite a lot last time about the behavior of what happens when I have moving charges. In particular, we were looking at the situation of two current carrying wires running parallel with the currents traveling in the same direction to the left, which actually meant that the electrons inside would be moving off to the right. And what we observed was that due to some interesting length contraction effects, the densities on the different wires would change in such a way that the moving electrons in the upper wire would find themselves attracted to what they would see and observe as a positively charged wire down below them. So if all the electrons are feeling that kind of a downward force, we can expect, and this is precisely what is observed in laboratory experiments, there to be a corresponding attraction between those two wires. Now, we then gave a very in-depth analysis of all of what's happening relativistically. So I thought I'd give just a brief review, because there's a lot of conceptual ideas involved there, a brief review of what it is that's actually going on that leads to this attractive phenomenon. Then we will go and look at what our final summary was in terms of the actual specifics of the form of the forces. And then in this lecture, we'll begin to develop the concept of some new kind of a physical entity that must be out there, some new kind of a field in order to explain the phenomena that we're observing. So, if you recall, last time we were doing a relativity analysis, which means you always have to be very careful about everything that's going on and what it looks like in one reference frame versus another reference frame. In this particular case, in the laboratory view, we were looking at what we see in the laboratory when we have these two parallel current carrying wires. The lower wire we actually had taken out very explicitly in our diagram. So here we are standing stationary with this stationary lower wire. And then what we further did is we took one electron from the upper wire and we just focused on it. So here's then the setup that I'm going to use, right? We're going to be the stationary observer 1, representing the laboratory view, the laboratory reference frame. We'll have a coordinate system, the y-axis vertical, the x-axis horizontal. In this wire, then, we have these stationary positive charges, the nuclei. And because the current's going off to the left, what that means actually, if it's a normal metal, there are electronic negative charge carriers moving off to the right with some velocity, which in this case I will call v sub x. This wire, of course, likes to maintain itself nice and neutral as the electrons are conducting through it. So that means then that the spacing between the negative and positive charge carriers are the same for a neutral wire, and they're all sitting then at separation d. Now, as for the electron that's moving in the upper wire, the one we've decided to focus on, we can imagine we have a moving observer, numbered 0, right, riding on that electron as it moves along with a constant velocity vx off to the right. But what we are about to see is that it's going to experience some additional force that's going to try to attract it down towards the lower wire. The origin of that force we can see when we transform this set of observations to how things would look actually in the electron's rest frame, or from an observer riding on that electron. What that observer would first see, of course, traveling off here to the right, is that the person standing in the laboratory frame suddenly is moving towards him to the left at velocity v sub x. Moreover, when our observer looks downward, right, to look at the wire down below, in the original reference frame, we had a series of stationary charges, positive charges at distance d, but now we are riding with an observer who is traveling past those stationary mile markers. So in that moving observer's frame, where they feel that they are not actually moving, but what they will observe then are these positive charges then also moving past them, right, with velocity v sub x off to the right here like so. But as we had talked about earlier with Sally and her trip to Alpha Centauri, her observation, or this observer's observation, will be that those mile markers now appear closer, with the lengths contracted by a factor of gamma. There's another somewhat more subtle discussion that involve the fact that now in this reference frame, from the electron's point of view, the electron is riding along at the same velocity with these negative charges, right? So these are actually stationary in this reference frame. And from this perspective, it is the laboratory observer who is moving past a series of mile markers, so that when that laboratory person actually observes them in his own frame, he's going to see their lengths contracted, which means that their home length in the frame where they are stationary actually is larger by a factor of gamma. Either way you look at it, the clear thing is that the positive charges are now more concentrated on this wire than the negative charges in this reference frame. So from this negative charge's point of view, he's looking at a positively charged wire down below, and so we'll feel an electric force and an attraction towards that wire and would then begin to accelerate. When we map that acceleration back to the home reference frame, there may be some time dilation effects that we would have to factor in if we wanted to do all the math very carefully. We would have to try to take into account any shifts in the mass of the electron between the two reference frames. And when you do all of that, at the end of the day, when you're very careful about everything, what you end up concluding is that there is a force on a moving charge up here. This negative charge feels the following force. And I should be careful, actually. Last time, I forgot that we were talking about negative charges, right? And so I ended up with my axes pointing in the wrong direction. I now have all of the signs completely correct here in this expression. The force in the y direction, of course, with the y pointing up, is going to end up being negative because I have a negative charge and electron. So the net force would be downward according to this formula, exactly as we see here in the figure. So this is the correct formula. We find that the force then is in the y direction. It is proportional to the charge, the velocity divided by c squared, and then when you work through all the other factors, we can see the essence of the electric field from a wire coming in with this famous factor from Gauss's law, 1 over 2 pi r epsilon naught. So that's what we then see then here in the laboratory view. That's the origin then of the force that we feel. So that's the basic relativistic underpinnings of the effect that we are trying to unravel in more depth today.